The study of parabolic coordinates represents a sophisticated intersection of geometric theory, computational modeling, and physical reality. These systems are defined by families of interlocking curves that share a single central focus. The primary appeal of this framework lies in its orthogonality, a property ensuring that coordinate lines always intersect at perfect right angles. This geometric secret sauce simplifies complex physical equations, allowing researchers to break down multidimensional problems into independent, manageable components. To move from a two-dimensional plane to three-dimensional space, this system utilizes two primary construction methods. The cylindrical model. This approach extrudes 2D parabolic grids linearly along a straight axis to create nested, trough-like structures known as parabolic gutters. The rotational model. This method spins the 2D curves around their central axis of symmetry, forming a series of nested, bowl-shaped shells or paraboloids. One of the most significant applications of the system is in the study of the Stark effect, which examines how external electric fields shift and split the energy levels of atoms. While standard spherical models struggle with the directional nature of an electric field, parabolic coordinates align naturally with the field symmetry. This alignment reveals how a symmetric electron cloud becomes distorted and asymmetric, stretching along the axis of the field. In extreme cases, this stretching creates a pathway for the electron to escape the atom entirely, a process known as field-induced ionization. By using these coordinates, the complex three-dimensional equations governing an atom are transformed into a solvable set of one-dimensional equations. In engineering, the focal properties of parabolas are utilized to manage electromagnetic waves. Parabolic reflectors, commonly used in satellite dishes and radar, are designed so that all incoming signals parallel to the central axis reflect toward a single, sweet spot at the focus. This geometry ensures phase matching, meaning that signals traveling different paths to the focus arrive at the exact same time, maximizing the gain and efficiency of the antenna. Specialized off-axis mirrors further refine this by isolating a section of the parabola away from the center, allowing sensors to be placed at the focus without blocking the incoming light or signal path. Parabolic shapes are highly favored in high-speed aerodynamics for the design of rocket and missile nose cones. These shapes minimize drag by allowing fluid streamlines to wrap smoothly around the hull without sharp breaks. At the very tip of the cone, known as the stagnation point, incoming air stops instantly, creating peak pressure and intense heat. This creates a thermal boundary layer that clings to the vehicle's skin. At extreme speeds, this layer is pinned tightly against the surface by atmospheric compression, while at slower speeds, the heat diffuses further into the surrounding air. The system is also the natural choice for analyzing how energy behaves near sharp points or knife edges. In electrostatics, this is demonstrated by the lightning rod effect, where electrical charge aggregates heavily at geometric points. Visualizations show that voltage lines crowd together tightly near a sharp tip, indicating a massive local increase in electric field intensity. Beyond physical applications, the study of these coordinates supports deep theoretical concepts such as coordinate invariance. This principle demonstrates that while the mathematical system used to describe a field may change, the underlying physical reality, such as gravity or an electromagnetic field, remains consistent. By moving from standard cylindrical or spherical systems into the theoretical peak of parabolic geometry, researchers can verify fundamental identities that remain stable regardless of the observer's perspective.